last lecture we started on talking about total variation diminishing schemes. So we started on good enough schemes, which is only first order. And we discussed the reconstruction schemes that can get us second order. But the good enough theorem basically says that if you naively perform a reconstruction to get yourself to second order, it is impossible to have a physical solution that is total variation diminishing. So you have to create oscillations or new extremas unless you use a nonlinear scheme to solve even a linear equation. So today we are going to be talking about how to use a nonlinear scheme to solve even a linear equation. Okay, so here let's consider just a very simple equation, partial u partial t plus partial u partial x equal to 0. That's like the simplest equation we can think of. We can solve it using finite difference, but here we are going to solve it using finite volume. And we are going to find out even on this simple equation, without a nonlinear mechanism, we can't solve the linear equation using finite volume that do not produce new oscillations. Okay, so that's what we are going to be talking about today. The reason that we actually create new oscillations in finite volume context is because of this. Let's consider a local extrema. So let's consider a solution like this: u as a function of x. Okay, we have a discontinuity over here. And for this simple equation, for this linear advection equation, how is the equation going to evolve? What should the analytical solution behave?
Characteristics along x equals t.
It should move towards the x direction, positive x direction, at a constant speed of 1. So the discontinuity should not change its shape, right? The maximum, the left-hand side of the discontinuity should stay the same value. The right-hand side should stay the same value. Nothing is going to be going above the left value. Nothing should go below the right value. But now let's consider a reconstruction. So in a finite volume scheme, let's say we have a solution that looks like this over here. Okay. And let's take a look at the finite volume approximation of this. We are going to get a constant. We are going to get a volume average to be like this here. We are going to be getting a volume average like this here, and we are going to get a volume average like this here, right? Okay. So let's use the scheme we used on Wednesday to perform a reconstruction. Okay, so we have, let's use a red color to represent the reconstructed value. And particularly, we want to look at what is the reconstructed value from this cell, because that's what's the most interesting. If you look at other reconstructions, we are going to get basically constants, right? Okay, so now let's look at here. Let's look at, for example, this interface to see what our reconstruction is. Remember, we are going to take the cell average value as an approximation of the cell center value. We are also going to take this cell average as our average of the cell center value. We are going to perform an extrapolation, which is going to get us to here. Okay, that's good. There is no problem about that. Now let's consider the reconstruction here from the same cell, but on the left-hand side of this interface. Again, we are going to use the same cell center value approximation here. We are going to use a cell center approximation here. And now when we extrapolate, we may get something here, all right? That is actually lower than the lowest value in the continuous solution. So if you take the real solution, the analytical solution, perform a volume-wise average, and then perform a reconstruction from that volume-wise average. The reconstructed solution can go beyond the original minimum and maximum of the solution. Does that make sense? Okay, that's fine. And even a worst case is here. So imagine I'm now trying to reconstruct the value here from the right-hand side cell. And now I'm using these two values to perform this reconstruction. That's horrible, right? I'm reconstructing a value that is as high as here. So that's like far beyond what the value of the function should be. And that's a problem. That is the primary reason why we are getting non-physical oscillations. The solution, numerical solution, exceeds the value it should be in the analytical solution. This thing is the primary cause of the non-physical oscillations. So extrapolation is bad. It is bad especially near discontinuities or near local minimums and maximums. So the reason this is bad is because this is actually local maximum, right? If this is not a local maximum, if the adjacent value to the left is even higher, actually this reconstruction is fine. It is actually more accurate than the piecewise constant approximation. But the fact that this is a local maximum makes it problematic. That's the motivation of a limiter. The limiter is saying that extrapolation, reconstruction by extrapolation is good if you have a very smooth region, if you are in a very smooth region. But extrapolation is bad if you are near a local maximum or local minimum. So here's the nonlinear mechanism we are going to introduce. It is a mechanism that detects local minimum and maximum. If a cell average is higher than both its left neighbor and right neighbor, I'm going to declare this as a local maximum. And I'm going to turn off the extrapolation and fall back to the piecewise constant approximation. If I detect this is a locally very smooth region, if the delta of this cell average to the left cell average is approximately the same as the delta from this cell to the right cell average, if it's pretty much a linear region, then I'm not going to use a piecewise constant approximation. I'm going to use the extrapolation. So that's the whole idea of the limiter. It is a nonlinear mechanism because it is going to do completely different things depending on if the local solution is a local minimum or not. And also we want to do this in a continuous way. We don't want to have a sudden switch. Okay, a sudden switch is usually bad in numerical methods. It is going to create, so you have a continuous PDE, right? You don't want to discretize into an ODE that is discontinuous. Anything discontinuous in the ODE sense is going to ruin the order of accuracy in terms of the time integration. Or the time integration kind of assumes the ODE itself is smooth and continuous. So we don't want the ODE to be discontinuous in the sense that, like, if the solution is above a certain value, the right hand side is, the f of u is completely different from when the u is at just below a threshold. So basically we want a smooth and at least continuous mechanism to switch the behavior from an extrapolation to a piecewise constant when I switch from a locally smooth region to a local maximum and minimum. That's the idea of the limiter.